So in this video, I'm going to take you through this sheet, the vector equation of a line sheet. I'm going to go through it on the whiteboard software. So if you could find the sheet to go along with that one as we go, it will be much easier than me flipping backwards and forwards through each one. But please make sure you have this sheet next to you whilst you watch the video. So in the first question, we're given a line on a coordinate system, and we need to find the equation of the line in the form y equals mx plus c. Hopefully from last year you remember that in this form m is the gradient and c is the y-intercept. If you didn't remember that though, what you could do is you could choose 2 points that you can see for x and y, put those in and then find n and c. So for me, the most obvious point on the line would be the point at 0, 2. At this point, x equals 0 and y equals 2. So 2 is equal to m times 0 plus c, which means that 2 is equal to c. So we've done that one. The second most obvious point on the line would be at -1, 0. And now we don't have y equals mx plus c, but y equals mx plus 2. So y is 0 equals m times -1 plus 2, which means we can easily find out what m is. We have 0 is minus m plus 2. I'm going to add m to both sides and get m is equal to 2. So y is equal to 2x plus 2, and that shouldn't come as any surprise because the graph crosses the y-axis at 2, which is why this is 2, and the gradient's 2 because each time you go along 1 in the x direction, you go up 2 in the y direction. So, using this equation that we have, our next job is to find out if the point 3, 9 lies on this line. So if x is 3, is y equal to 9? Well, let's see. Y is 2x plus 2, so 2 times 3 plus 2. So when x is 3, y would be 6 plus 2, which is 8, which is definitely not 9, so no, it doesn't. Then we need to find out if x negative 2 is on the line, what is x? Well, this is our y-coordinate. -2 is equal to 2x plus 2. I'll take off 2 to get -4 is 2x. Divide by 2 to get -2 is equal to x. So I found then the point -2, -2, which, if you look at the line on the coordinate system, looks like it could work as a way of checking our answer. Number 2, I will tell you how to do, but I won't show you how to do it, because this is something we've done relatively recently. You need to find out if the vectors are parallel to one another, and you should remember if two vectors are parallel, then there exists a scalar r for which a is equal to r times vector b. So one is a scalar multiple of the other one. So you need to find an r that works for the top row, let's say, and see if that same r works for the bottom row, because of course two sides of a vector equation like this are only equal if both components are equal. So I can tell you that the answer is that b is parallel to c. So check those and see, and then check one other one to see that you can't find an r, just for a little bit of practice in preparation for your first test. In part 3, you're asked to find the midpoint of the line AB if a is equal to 7, 5, and the vector from a to b is equal to -4, -8. So the midpoint of this line AB would be our start point. Endpoint is start point plus instructions. Now I don't want to go all the way to b, so I don't want the whole vector. I just want half of the vector a to b. So I have 7, 5 plus a half times negative 4, negative 8. And it's worth just taking a little bit of time over this part, because I know some of you are still struggling a little bit with multiplying fractions with vectors, so I'll take this part slowly. 7, 5 plus negative 4 times a half, negative 8 times a half, because when I multiply a scalar by a vector, I multiply each of the components of the vector by that scalar. So I have 7, 5 plus negative 4 times a half. I could also put in a denominator of 1 there, and cancel is negative 2, negative 4, which is 7 take 2, 5, 5 plus negative 4 is 1. So 5, 1. And you could check this by just doing a little sketch if you wanted to. For B, we're given A and B, and I'll leave that one as an exercise to you, remembering that the formula for the midpoint is a half times A plus B, if you have the coordinates of 2 points. And you can put those in there, multiply what you get by a half, the process that we did here, and you should get your midpoint out as being 5 halves and minus 7 halves. So 2 fractional components to your vector there. So that's the warm-up done. Let's move on then to the bulk of what we need to do. So you're asked to draw a line, P to Q, and you're given the coordinates of P and the coordinates of Q. And it asks you to think about going from P to Q, where on the line is your pencil if you've drawn a third of the line. Now finding a third of the line is very similar to what we did here with finding a midpoint. You could do P plus a third from P to Q to find out the coordinates. You could also plot this on a coordinate system, measure out the line from P to Q, divide that length by 3, and see what a third of the way is along, and you could then compare that answer if you wanted to with the answer you got by doing it this way as we did before. 3/5 of the line is a very similar process, and then in C what I wanted you to do was to generalize that to any kind of portion on the line. And this here is our main new point. So if x is any point on the line, then in A, x, the point x, can be represented as start, P, plus instructions, a third of the way from P to Q. And for B and C, then you'd have x is equal to P plus 3/5 of P to Q. And in C, you'd have x is equal to P plus T times P to Q. And that is the equation that I really wanted you to get to. So x is equal to P plus T times P to Q. This is one form of the vector equation of a line. And it's based on what we've been practicing a lot over the course of our work with vectors, that the endpoint is equal to the start point plus instructions, where the instructions are built up of this vector here, which gives us which direction we go in, multiplied by a scalar t, which can make this whole part bigger or smaller, so that's how far we go. So the magnitude, that controls the magnitude of this vector of these instructions. So I know in which way I'm going, I know then how far I'm going to get there. I add that to my start, and I end up at some point x. So, in this definition that we had up here, t has to be within the interval 0 to 1 if I want to stay between P and Q. However, I can generalize this definition even further. I can say that for any line G, I have any point on that line can be given by taking a starting point on the line, a point that I know, and adding some multiple of a direction vector g that goes in the direction of that line. So it's a new way of defining lines using vectors. Therefore, this is a vector equation for the line shown above. And you can see why, because 0, 2 is quite clearly a point on that line, if you have a look at where it crosses the y-axis, plus t, so some scalar, multiplied by the direction vector of the line 1, 2. And you can see that 1, 2 works as a direction vector for this line. As if I want to go from here to here, I go 1 along, so 1 in the positive x direction, and 2 up, 2 in the positive y direction. And this works for any start point and any direction vector that goes in the same direction as the line. I could have also taken -1, -2. So if you start from any point, it just means you go in the other direction along the lines. And then if we just change t, so here I ask you to substitute t is 0, 1 and -1 into this equation, and check that the points that you get for x lie on the line. So if, for example, t is equal to 1, then I have 1 times 1, 2, which is of course 1, 2. Then I do 0 plus 1 is 1, 2 plus 2 is 4, and so I get the point 1, 4, which isn't quite here, but you could see that would work on this graph that I have. And I've already explained to you where p and g have come from. And on the other side, you have some exercises to cement this knowledge. And as I've mentioned, this vector equation is not unique. Any starting point, so any point that you can see on the line, and any direction vector can be used. So you'll find that you can have infinitely many vector equations of the same line, because there are infinitely many points on the line you could use. And any multiple of this vector works. It just takes you further along the line if the components are bigger, for example, and then to get to a point closer, you'd need smaller values for t. That means that I'd always recommend having integer values, if possible for the starting point, which it should be possible at least one point on the line, and also choosing your direction vector so that that has integer values too. I'll leave the other exercises on this sheet as an exercise for you. If you weren't in this group, try a couple of them before Friday, but you don't need to try all of them before your work together on Friday. I'd recommend though that you do try most of them before the test next week. If you have any questions, please note them down. And then first of all, your first line of inquiry in that case would be to ask members of the other group to see if they can explain it to you. If not, then of course you're very welcome to come and ask me.